This is a multiple-choice question testing your knowledge of the scikit-learn multidimensional scaling (MDS) functions parameters. You'll need to identify the correct statements about how these parameters work. This statement is correct. The "random underscore state" parameter in MDS sets the seed for the random number generator. Using the same "random underscore state" each time you run MDS will give you the same results. Think of it like a recipe. The same ingredients and instructions will always produce the same cake. While the final visualization might look slightly different, it'll be consistent, allowing for easy comparison of results. Incorrect. The "metric" parameter doesn't simply need to be set to "true". It specifies whether you are providing a distance matrix or raw data. If you've already calculated pairwise distances, you set it to a specific metric or "pre-computed" accordingly. Setting it to "true" is only relevant in cases where your algorithm is computing the distances from the raw data. Partly correct. "n underscore components" determines the dimensionality of the reduced space. Setting it to 2 gives you a 2D representation. However, remember that you will need a separate visualization tool, such as Matplotlib, to actually see the graph. MDS only does the calculations and does not plot the data itself. Correct. If you're already providing a dissimilarity matrix, a matrix containing pairwise distances between data points, you must tell MDS by setting "dissimilarity" to "pre-computed". This tells the algorithm that you've done the distance calculations already. Otherwise, MDS will try to calculate distances itself and might give you unexpected results. This line simply serves as a heading or section title for the parameter choices discussed in the questions. It doesn't require further explanation. This title introduces the topic of the quiz, which is to understand how the parameters of the scikit-learn's multidimensional scaling function, (scalearn) manifold MDS work. Let's dive into the fascinating world of dimensionality reduction. I see this parameter controls the randomness in the multidimensional scaling MDS algorithm. Think of it like setting the seed in a random number generator. A fixed value ensures you get the same results every time you run the code, making your analysis reproducible. This is mainly useful for comparing results across different runs or sharing your work with others. It doesn't drastically change the final arrangement of points, but rather ensures consistency. This parameter tells the MDS algorithm what kind of data you're giving it. If you provide a pre-computed distance matrix, which shows the distances between all pairs of data points, set this to pre-computed. If you give it the raw data points themselves, MDS will calculate the distances. It's crucial to use pre-computed when you already have a distance matrix. Otherwise, you'll get wrong results. This one's straightforward. It determines how many dimensions you want to reduce your data to. For instance, if you set it to 2, you will get a 2-dimensional representation of your data, perfect for visualization on a 2D plot. It's the target dimensionality of the reduced space. Here, you specify how the distances between data points are calculated. If you set it to true, then MDS uses a standard distance metric, like Euclidean distance. If you already have a distance matrix, and thus set dissimilarity to pre-computed, you don't need to define this parameter because MDS already knows the distances. I'm explaining the parameters used in scikit-learn's multidimensional scaling MDS function. MDS is a technique used to visualize high-dimensional data by reducing its dimensions, usually to 2 or 3 for easy plotting. We'll focus on understanding how to use the parameters to control this process. It's like making a map of a complex city, showing the relative distances between landmarks but in a simpler, easier to understand way. This section presents a multiple-choice quiz to check your understanding of the MDS parameters. You'll be asked to identify correct statements about how the parameters work within scikit-learn's MDS function. Let's see how well you understand the MDS function. This parameter determines the dimensionality of the reduced data. For example, "n underscore components equals 2" means the algorithm will output data in 2 dimensions, suitable for a 2D scatter plot. Think of it as choosing how many dimensions you want your simplified map to have. It's crucial for controlling the visual outcome of the dimension reduction process. This parameter tells the MDS function what kind of input it is receiving. If you're giving it a pre-calculated distance matrix, showing distances between all pairs of points, you set dissimilarity equals pre-computed . If you provide the raw data points, then you'll leave it at the default value or set it to false . This is a simple but essential parameter for using MDS correctly. This parameter is for setting the seed for the random number generator. In MDS, some computations might involve randomness, especially if starting the calculations in different ways. Using a random_state ensures the results are reproducible across different runs. If you set this to a specific number, you will always get the same result. It's key to ensuring that your analysis produces the same outcomes each time. This parameter specifies how distances between data points are calculated. It can either be a built-in distance metric, e.g., Euclidean distance, or a pre-computed matrix. If you are using a pre-computed distance matrix, you need to specify it through the dissimilarity parameter. Setting metric to true or false doesn't affect accuracy on its own. It's about how distances are computed, not if they're accurate. I'm going to explain the parameters of scikit-learn's multidimensional scaling, MDS, function. MDS is a powerful technique to visualize high-dimensional data by reducing its dimensions. We will focus on understanding how to configure these parameters for best results. MDS can work with two types of input. You can feed it a dissimilarity matrix, which directly provides the pairwise distances between data points. Alternatively, you can provide the raw data points themselves, and MDS will calculate the distances using a specified metric. This parameter tells the MDS function that your input data is a pre-computed dissimilarity matrix, meaning you've already calculated the distances between all pairs of data points. If you set this to pre-computed, then you must ensure that your input data actually is a distance matrix. N_components parameter lets you control the dimensionality of the output. Setting it to 2 means that the MDS will reduce your data to 2 dimensions, which is perfect for creating a 2D visualization. You can visualize the data on a scatter plot. The random_state parameter is used for reproducibility. Some aspects of MDS involve random processes, so using a fixed value for random_state ensures that you'll get the same results every time you run your code. It does not affect the accuracy of results, just the specific arrangement of the data points, which makes it easier to compare analyses. Once you feed in the data and specify the correct parameters, MDS performs its computation to reduce the dimensionality of your dataset. It applies algorithms to create a new representation of your data which preserves the important distances. After the computation, you have a 2D representation of your high-dimensional data. You would then use other tools to visualize this. For example, a scatter plot can show the positions of your data points in this new 2D space. I'm going to explain the multidimensional scaling, MDS, function in the scikit-learn library. MDS helps us visualize high-dimensional data by reducing it to fewer dimensions, often 2D for easy plotting. We'll focus on understanding its key parameters. This is a multiple-choice question testing your knowledge of the parameters within the scikit-learn Manifold MDS function. The MDS process involves taking a dissimilarity matrix, representing distances between data points, or raw data, and transforming it into a lower dimensional representation while trying to preserve the distances as much as possible. This statement is correct. The dissimilarity parameter tells the MDS function whether you're giving it a pre-calculated distance matrix or the original data points. If you already have a distance matrix, set it to pre-computed . Otherwise, MDS will calculate the distances itself. This is absolutely true. Setting a fixed random_state is like setting a seed for the random number generator. This ensures that you get the same results every time you run your code, making it reproducible. Although the arrangement of points might differ slightly, the overall structure of the visualization should remain consistent. That's incorrect. The metric parameter doesn't directly relate to accuracy. Instead, it specifies whether you are providing a distance matrix or raw data to the algorithm and what type of distance to use between points if using raw data. Partially correct. N_components controls the output's dimensions. Setting it to 2 gives you a two-dimensional representation. However, you'll need a separate plotting library, like Matplotlib, to actually create the visualization. The MDS only provides the points in the reduced dimension, it doesn't automatically plot them. I understand this section as the overall topic of the quiz. The quiz focuses on testing your knowledge of the parameters used in scikit-learn's multidimensional scaling, MDS, function. MDS is a technique used to reduce the dimensions of your data, while trying to preserve the distances between data points. This is the core question of the quiz. It presents multiple-choice statements about the parameters within the scalearnmanifold MDS function. I need to evaluate each statement's accuracy. I'll be testing my knowledge on 4 specific parameters. This section indicates that I should consider how the parameters relate to each other and to the input data. The interaction is important because they define the way the MDS function works. This highlights the 2 ways I can give data to the MDS function. Either as a pre-computed distance matrix, showing distances between all data points, or as raw data points. I need to decide which type of input I have before selecting the appropriate parameters. This is a parameter value. I use this setting for the dissimilarity parameter when my input data is a pre-computed distance matrix. This tells the function that I'm providing distances, not the original raw data. This is a parameter. N_components determines the dimensionality of the output from MDS. For example, N_components equals 2 gives a two-dimensional representation of the data, suitable for visualization on a 2D plot. This is another parameter that controls the random number generator. Setting this parameter to a specific number ensures I get the same results every time I run the code, reproducibility. Even though minor variations in the visualization's appearance might occur, it guarantees consistent results. It's like setting a seed for a random number generator. The metric parameter determines how distances between data points are calculated if I give raw data. I set it to true to use a standard distance calculation, like Euclidean distance, or provide a custom distance function. If I'm using a pre-computed dissimilarity matrix, then this parameter is irrelevant. It's not a question of accuracy, but rather a choice between using a standard distance formula or a custom one. This is the output of the MDS function. It is the lower dimensional representation of the data, as specified by N_components . This output could then be used for visualization. I'm focusing on the scikit-learn, library's multidimensional scaling, MDS, function. It's a technique I use to reduce the dimensions of data while trying to preserve the distances between data points. Think of it like making a flat map of a curved Earth. I lose some accuracy, but I gain a simpler representation. The MDS function has several parameters. These parameters let me control different aspects of how the dimensionality reduction happens. For example, I can specify the number of dimensions I want to reduce to, or I can tell it whether I'm giving it raw data or a pre-calculated distance matrix. Knowing how to use these parameters correctly is key to getting good results. This is a multiple-choice question testing your understanding of the MDS function's parameters. Each choice presents a statement about a specific parameter, random_state, metric, N_components, and dissimilarity. I need to determine which statements are factually correct based on my knowledge of how these parameters work. This is the overall topic of the quiz. I'm excited to test my understanding of how to use the parameters within scikit-learn's multidimensional scaling, MDS, function to visualize high-dimensional data. This statement is mostly true. The random_state parameter seeds the random number generator. This means I get consistent results each time I run the code with the same seed, making my results reproducible. While it might slightly alter the arrangement of points in the visualization, the primary benefit is reproducibility. This statement is false. The metric parameter actually decides whether I'm giving the function a pre-computed distance matrix or raw data. Setting it to true simply means I'm using a standard distance metric, not that it inherently provides accurate results. The best choice for metric depends entirely on what kind of input I have. This statement is partially true. n_components does control the dimensionality of the output. Setting it to 2 means I'll get a two-dimensional representation of my data. However, I need to explicitly use a plotting library, like matplotlib, to create a 2D visualization from the reduced data. This statement is completely true. If I already have a dissimilarity matrix, a matrix showing the distances between all pairs of data points, I set the dissimilarity parameter to pre-computed to tell the MDS function to use it. Otherwise, if I give raw data, MDS will calculate distances itself.